semester's over for one of us. As you can see, things did not go well on this exam for me. It went great for you, just not so much for me. I was very, very proud of the fact at Montana State University towards the later years that I could peg an exam average at 75 every time, that I just could write an exam so that the average was going to be 75. And that's because I had a whole lot of experience with students at Montana State University. Clearly, I have not yet fully appreciated your talents because you had your way with this exam. As you can see, 183 of you got an A on this exam. There were 10 perfect scores, a whole lot of nearly perfect scores. So well done you. If you are one of those individuals who didn't do well on this exam, you need to go back and figure out what went wrong. Because this section of the class on dynamics, on forces, is the foundation for everything going forward in 105 and 106. And so if Newton's second law is still a mystery to you, the rest of the course isn't going to go well. I sent you an email this morning giving you a link to a video recording of me going through all of the questions on the exam and explaining how to solve them. So I encourage you, if you didn't do well, to go and watch that video and see if you can figure out where you went wrong. Given that I'm going to do this demo today, would someone be willing to give a really good prayer? Yes, please.
Grateful for the day, for talent with teaching and certain ability to teach concepts that are difficult. We ask that we might have the strength and try to learn these concepts, and we ask that we might be able to go forth with ceremony for this university and for the special opportunities that we receive because of being students at Brigham Young University. We have, and we say these things. Amen.
Amen. Thank you. Is it Sydney? Okay. I can remember something, just not everything. Okay, before we do the bed of death, let's take some attendance. Okay. Now you can click. Okay, last call. Get your attendance point. Okay. So let's look at this problem from your homework. This is the homework that's due Friday. It's the bobsled jump problem. Now, back in 2002, when we had the Winter Olympics in Salt Lake or up in Park City, the wonderful students of BYU volunteered in huge numbers as essentially officials helping people get to where they need to go. My son, my oldest son, was a student at BYU and volunteered, got a really nice jacket out of it. In 34, we're going to have that opportunity again for those of you that are on the longer track. Going to stick around for a PhD. Anyway, my youngest son wanted to go and participate, and I had to work, so my dear wife took him down, and the only tickets that my oldest son could get was to the bobsled. And he came back so excited about that bobsled that I had to write this exam question. And what you have is the Jamaican team. If you haven't seen Cool Runnings, that's part of your homework. Go watch Cool Runnings. Jamaica's got a bobsled team. Anyway, they compete by going down this frictionless half circle and launching off of that ramp and landing on this level landing field below. And the radius of that frictionless bowl was 100 meters. And the first part of this question that was only worth 2 points, and that should have been a dead giveaway, is how much Verk, we misspelled it there, if any, is done by the ramp on the bobsled as it moves from point A to point B. Now, again, it's a frictionless ramp, and so you know the answer is 0. Now, if we draw a free body diagram for the bobsled with the team, I have the force by the earth on the bobsled, but that's an internal force. We always include the earth, by which we mean the gravitational force, in our system, so that we can talk about gravitational potential energy. We never calculate the Verk done by the gravitational force. That's internal. However, this normal force by the ramp is an external force. We leave the ramp outside of our system, but it doesn't cost us anything because the normal force by the ramp on the bobsled is by definition perpendicular. That's what normal means, perpendicular to the track. And the motion is always going to be along the track. So these are always perpendicular to each other, giving me 0 Verk. And it doesn't matter where I look. The normal force is always going to be perpendicular. The motion is always going to be parallel. They will always be perpendicular. So I will have 0 external Verk. That means the mechanical energy, the total energy, is conserved. So let's do the hard part of this problem. The mass of the Jamaican team, including the bobsled, is 800 kilograms. If they're traveling at a speed of 50 meters per second over 100 miles an hour, when they reach point B, find the spring constant for the spring. And we remind you that the spring was compressed 4 meters. That's a big old spring, okay, before the launch. Now, we use buckets here. And since we know everything about the energy at B, and we want to know something about the energy at A, we choose those to be our initial and our final locations or events. So let's go to A and ask the questions we always ask. Is anything with mass moving? No. Okay, so there's nothing in the kinetic energy bucket. Second question, is anything up off the floor? Well, yeah, it's up off the floor. Indeed, it's 120 meters up off the floor if I choose the lowest point as my floor. Are any springs stretched or compressed? Oh, yeah, a lot, okay? And so the combination of those 2 buckets gives me my total energy. Now, if that's conserved, that just means it stays the same, whether I'm at A or B or halfway in between. But now, where is that energy? I asked the same 3 questions. Is anything with mass moving? Oh, yeah. Is anything up off the floor? A little bit. Any springs stretched or compressed? Not anymore. So that's what we have. And I write it in this form, potential energy spring plus potential energy gravitational at A has to equal the kinetic energy at B plus the gravitational energy at B. Now, if I plug in my formulas, this is what I get. Now, folks, up until now, on the exams, I've given you all the equations that you've needed for the exam, right on the front page. Because I feel, it's about learning how to solve problems, not about memorizing. If we wanted you to learn how to memorize, we'd be teaching you botany or stamp collecting, okay? This is an exception to that. What I find is if you don't know those formulas for the different kinds of energy, you don't recognize the players on the field. It's like me watching a soccer game. It's a waste of time. I have no idea what they're running around for, okay? So you need to know what these definitions are, these equations are that fill the bucket. And they're not, listen to my words. They're not going to be on the front of the exam. And when you go to the proctors in the testing center, they're going to just look at you funny if you ask for them, okay? So you've got to memorize them before the exam. You just as well do it today, okay? Now, here I've got some bad news. I've got K in red because it's the only thing that I don't know. I have numbers for everything else. I have numbers for everything else. Now, if that looks intimidating to you, if that looks like, oh, how would I ever figure out what K is? You need to practice, because these energy problems very quickly turn into messy algebra. That's not just an exception, that's the norm, okay? First real question is, can I cancel that mass? Can I get rid of that mass? Yes or no? Or heck no? Heck no, because it's not in this term. In order to cancel something, it has to be in every single term. I only bring that up because I see that mistake over and over and over again. Don't let it be you, okay? Now, if I crank and grind that equation, what I get is 25,000 newtons for each meter. That is a significant spring, okay? Now, because we don't do any work with a frictionless track, this gives us an opportunity to go back and review what we learned about centripetal motion, circular motion at constant velocity. Now, this is certainly not constant velocity, but right at the bottom, it's no longer speeding up, and it hasn't started slowing down yet. So I do know that right here, the acceleration is going to be perpendicular to the velocity or towards the center of the circle. So our formula for centripetal acceleration works at the bottom of a circular track, right here. And that is going to give me this formula from Galileo, v squared over r. If I plug in my speed and my r, I get 25 meters per second squared up.
Acceleration for centripetal force still works even if it's not a complete circle.
Yes, any part of a circle, because they don't know that it's not a complete circle. They haven't gotten there yet. Yeah. Oh, we're told in the problem that it's 50 meters per second right here. It was slower there. Yeah.
Okay.
Given in the problem. Okay. Now, the next part of this homework problem is asking you to find the magnitude of the normal force by the track on the bobsled, again at point B. If I'm looking for a force, any force, I start with a free body diagram. And I have the weight down, I have the normal up, and you notice that I drew that normal force bigger than the weight because I want this diagram to scream the acceleration and the acceleration is up toward the center of the circle. Now, by Newton's second law, I take the mass, I take the acceleration, the centripetal acceleration, and I get the net force of 20,000 newtons up. Is that my normal force? No or heck no. No, no, that is not my normal force. That's the extra force in the direction of acceleration. I have to calculate my weight. Since the mass is 800, the weight is 8,000 newtons. I need 20,000 more newtons than that. So my normal force has to be 28,000 newtons. Good sir in the back, if you can speak loudly, I might be able to hear you, but maybe not.
That's
Oh, that's an excellent question. Why not just choose this as my floor and make this 100, and then I wouldn't have to worry about that. And the answer to that is that this problem has a part E, which is when they land on the landing field. And I find that if you change your floor halfway through a problem, there's mistakes that can be made. So it's safest just to choose the lowest point right from the get-go. Okay, you get the same answer either way though. Okay. Now, how fast will the Jamaican team be traveling right before they land on the landing field, and will this hurt? Your gut says yes. This is an energy problem. At B, that'll be our initial event. It's certainly got kinetic energy. It has a little bit of potential gravitational energy, but the spring is no longer compressed. And so that's my total energy. Because we're always ignoring air resistance, there is no work done between point B and the landing, as long as we look right before they land. Never let them land. If they land, there's all sorts of negative work done by the snow. Messy, messy, messy. It's always right before they land. Okay? Now, I would have all of my energy, but now all of it would be in the kinetic energy bucket. I write down what I have, and I write the formulas for that. What about this time? Can I cancel out the mass?
Yes.
Yes, I've got it in every term, so I can get rid of that. And then if I multiply both sides by 2, I get that. And then when I solve for that by plugging in my numbers, I get 54 meters per second. Yes, it will hurt. Yes, it will hurt. Okay. Questions on that? Why is it always people in the back? People be down front. Like that? Right, because I've chosen my 0 of height to be down on the landing field. So they're still up 20 meters there.
People gotta get it.
Okay,
But they're, now they gotta.
okay. New topic. Let's talk about momentum. When I say that senator has a lot of momentum, or that freight train has a lot of momentum, or that idea has a lot of momentum, what does the word momentum tell you about the senator or the freight train or the idea? Talk to your neighbor. What does it tell you? What does it mean?
I feel like there's nothing slowing it. It's going.
Okay. Brave soul, raise your hand. What does it mean? What is it?
Oh,
Momentum. No. Oh, you're volunteering your neighbor? That's why we call him the assistant of death.
Where does mine say?
What's that? It started moving? Okay, they're moving? Okay. Other definitions?
Like the amount that something wants to keep continuing moving. The amount that it wants to keep continuing moving.
Oh, the amount that it wants to keep continuing moving. Excellent, yes, they're saying the same thing, but at a gut level, what physicists think of when we think of momentum is how hard it is to stop something. How hard it is to stop something, okay? And at a gut level, that works. How hard something is to stop. Now, Will, you volunteered to help me here. Will turns out to be an avid skateboarder. This is a picture of Will going down the street. Will, how fast do you go? He says 50 miles an hour. That seems high, but I have no reason to doubt him. No reason to doubt him. So Will is going down the street at 50 miles an hour on his skateboard. There's a Mack truck going also down the street 50 miles an hour right next to him. Which has more momentum, the Mack truck or Will? The Mack truck. Will the Mack truck always have more momentum than Will? No. You park that Mack truck at Albertsons, it's not hard to stop a parked truck. Okay? So it turns out that the mass matters, but it also depends on the speed. And it turns out that the formula for momentum is this. I apologize, but we use the word P for momentum. The P is silent, like pneumonia. Okay. And we use P for so many other things, power and pressure, and they made a mistake, but that's the letter that's used everywhere. Okay. P for momentum. Now, I want you to think of an example with your neighbor of something that is hard to stop, has a lot of momentum, but a very small mass. Tell your neighbor what you're thinking of.
Have to say that. Yes. You have to.
That's a right message. I'm pretty good. Amen.
Okay. What examples did you come up with? A bullet, okay, a bullet. 31 years in Montana, I never once got a different example than a bullet. And on the first week of hunting season, I also never had any students in the room. So it's the most common example given. Now, I went to high school on Guam. I've told you that before. And what we didn't have in Guam were glass windows in our houses. We had little metal louvers that the geckos could get in. And that's because what we did have everywhere were coconuts. And we also had tropical storms. And when a tropical storm would blow through the coconuts, well, it became a whole lot like cannonballs. And so, but when I first got to the island, they had just had a huge tropical storm. And my friends had pictures of telephone posts that had little things like pieces of glass and nails stuck into them. They were hard to stop because they were going very, very fast. Okay, it's the V, the V. Now give me an example of something that has a lot of momentum, hard to stop, that's not going very fast. Talk to your neighbor, come up with some examples there.
Stop, I do that for work.
Oh,
Every day. But some days. Okay, I've done it.
Okay. Raise your hand, Rachel. Where are you? Yes.
Elephants.
An elephant? Good example. Okay. And that's the one I chose, an elephant. Okay. This space shuttle, even when it's just lumbering across the runway, is hard to stop because of its huge mass. But of course, this is not the way a space shuttle's meant to be used. It's meant to be used going 17,000 miles per hour. Fast and big, okay? Very hard to stop. Now, I need some help here. What's your name? Reagan, okay. Reagan, do you own a boat? Okay, she has a boat and she's a captain and that's her boat. Ha, you're surprised that I had a picture of your boat. Okay. Captain Reagan, your job as captain is to park that boat, you know, to stop it at the dock. Now, one way to park that boat, to stop it at the dock, is to turn off the engine and let the water in front of the boat push on the boat and slow it down. Now, Captain Reagan, how long before docking should you turn off your engine about? How long before docking should you turn off your engine? A while, yeah, an hour, hour and a half, because it's going to take a long time for that water to slow down that huge ship. Now, have you known Captain Reagan for a long time, for most of your life? Yes. Would you say she's a patient captain? No, no. And she doesn't have to be patient. She can stop that boat in 23 seconds. How? Ram it into the dock. And 23 seconds later, in 3 city blocks, it'll be stopped. Okay? Now, here's the big idea. Stopping that boat means changing its momentum. That's what momentum means, is how hard it is to stop. And what we just discovered is that there's 2 different ways to do that. We can either do that with a small force if we're patient, if we have a lot of time for that force to act, or we can do it quickly with a large force. Now that combination, force times time, is what changes momentum. You remember what changed energy was force times distance. And this is different than that, okay? Force times time is what changes momentum. And we call that the impulse, that combination of force times time. Now, this simple formula, force times time, only works if that force is constant. If it's 50 Newton, 50 Newton, 50 Newtons, 50 Newtons, 50 Newtons. But you know that in real life, that's usually not the case. If I hit a baseball with a bat, I know that the force on the ball is going to ramp up to some maximum value and then ramp back down as the ball leaves the bat. So in that case, what we want is the average force. If we don't want to do calculus, and I think it's fair to say we don't, we just take the average force and multiply by the time that that force is applied. Okay? That makes sense? Okay, I have been dreading this moment. It is now time for the bed of death. That's my family. We're a handsome bunch. You're laughing at my family. That's assistant of death. Let's give Caden a hand, folks.
You gotta cancel.
Then you can move it. This was so much easier when I was younger. Okay. At this point, I am required by the university attorneys by law to offer the following warning. Do not, I repeat, do not try this at home. I am a trained professional. I have not always used 1,000 nails. I started out with 1 nail, worked my way up to 3 nails. Oh, that's not right. If we were to park my 120 pounds on 1 nail, here laugh. We, my considerably more weight on 1 nail, that would be biology, okay? That would be a hole. Having lots of nails, if I spread my weight over 1,000 nails, each nail is only pushing a little bit. And so that makes it so that I don't get a bunch of holes in me. However, that's not what would save my life. If I were to lay down on the floor and ask Caden to hit me with the sledgehammer, he'd do it. But again, that would be biology, okay? So there's something else that's going to be hopefully saving my life. And I want you to think about it as we go through this. Demo. I'm gonna. That would have been a mistake. Okay. Okay. So, now. A little longer. Right, first let's put the chest plate. Okay. Oh, what happened? It to lay flat. Cinder block of death. I would like to have it this way. Fine. Now, Hayden's never done this before, so I'm going to give him brief instructions. What I'm going to do is, I don't want to be breathing when you hit this. I do want to be breathing afterwards. I'm going to say ready and then hold my breath. And after that, you just swing with all your mighty might and hit the cinder block. Not my head. I'm ready. Ready. In the face. Okay. Explain it to do.
Probably a show that he has done.
Let me ask a question here. Oh, I had a grad student years ago who was as old as I was, and he was just coming back to grad school, and he had lost one arm in an accident when he was 16 years old. And anyway, he was so athletic. It looks like you've had taken a hard fall. I'm supposed to push this button if I want an emergency call. That's on you, Caden. Okay. Anyway, he would climb mountains, rock climbing with one arm. And so he insisted that he wanted to swing the sledgehammer. And so this was for a bunch of high school teachers. But during a class like this, we had another professor that was ready to swing the sledgehammer. And then Larry showed up in the back and said, "Wait, guys, you said I could swing the sledgehammer." And everyone turned around and looked at Larry and said, "Oh my goodness." But he had practiced over and over and over again. I want to show you how good he is. He could even do it in slow motion. Okay. Now, my question to you is, which way do we want to stop the sledgehammer? Do we want to do it with a little force, big time, or big force, little time? And I'm going to let you vote on this with your clicker. Just let me get you started. Okay, now you can click.
That's probably. Exactly.
Situation, yeah, that we want to make something not a-
Okay, get your vote in. This isn't rocket science. Oh, wait, it is. It is. We're gonna find out this is rocket science, okay? Last call. What did we say here? We said quickly with a large force. I guess that I should have asked this differently. I should have asked, which way do I want to stop the sledgehammer? Because I understand Newton's third law. And that is that if I put a big force on that sledgehammer to stop it quickly, it puts a big force on me to kill me. What thing saved my life? What piece of equipment saved my life? The cinder block. The cinder block should be called the cinder block of life, not the cinder block of death. Without the cinder block, we would stop that sledgehammer almost instantly. It would take a huge force. But as the sledgehammer crashes through the cinder block, it lengthens out the time and reduces the force. That cinder block was acting like a funny looking airbag, if you will. Okay. I needed that cinder block to break. The one time, well, one of the times that I got hurt doing this demo, I had a very strong fellow swinging the sledgehammer. I told him to swing with all his mighty might. He just smirked at me and said, "No, you don't mean that." And so he pulled his punch, hit me really hard, but didn't break the cinder block. And I felt that. But the worst experience I ever had was 32 years ago, the very first time I did it. I was a brand new green professor. And I went to an older professor and said, "Larry," it's a different Larry, Larry Kirkpatrick, the co-author of one of my books. I said, "How hard should they swing the sledgehammer? I'm worried that I might get hurt." And he said, "Oh, trust the physics, Greg. Just trust the physics. You'll be fine." So I went down to class and I found a student that I knew from church, an LDS student, and his name was Ralph. And I said, "Ralph, would you swing the sledgehammer?" "How hard should I swing?" "Hard as you want, Ralph. I'll be fine." I forgot to notice that Ralph was a giant of a man. And he took this great big roundhouse swing and he came down as hard as he could. and he missed the center of the cinder block. He hit the side where it was solid. My arms went up, my legs went up. I couldn't breathe. Half the class was afraid I was dead. The other half was afraid I wasn't quite. What do you do when your professor just sort of dead? You hit him with a rock, hit him with a rock, put him out of his misery. The other time this didn't go well, my oldest son and I were going to it was a road show. You were not old enough to know what road shows were, but it was a torture that used to be imposed on members of the church. And we were asked to do a in between the road show demo. And so we were going to bring the bed of death. And my son, who was 16 at the time, asked if he could lay on the bed of death. And his mother said, "Oh, no, you do not. Not my baby." But once we got in the car, my wife wasn't there. And so when we got there, he got on the bed of death. I swung the sledgehammer just perfect, crashed the cinder block. And he was so excited to be alive, he pushed himself up off the nails, and he had holes in his hands everywhere. And when I got home, I was in so much trouble. Gentlemen, what I'm saying is listen to your wives. Okay. So what I want to do is I want to stretch out the time so that the force is as small as possible. Now, there's another video that I am going to show. This is a little disturbing. I can't watch anymore, but this is a high school teacher, physics teacher, and he has asked the teacher in the room next door, who happens to be a history teacher, to swing the sledgehammer, except they don't have a sledgehammer, so they use a maul.
Oh.
Picture the eel of us.
We just had to do that to a dog we adopted from the kennel. Okay,
Imagine being in front of your high school class.
never trust a history teacher. Okay. Now, the grand equation of chapter 8 in our textbook is this one here, that impulse changes momentum, and an impulse is a force times the time. Now, there are certain situations where the change in momentum is fixed. There's nothing you can do about it. Okay, if you're going down the road at 20 miles an hour and you suddenly hit a big old brick wall, your change in momentum is what it is. And if you want to reduce the force, what you want to do is stretch out the time. So I would like you with your neighbor to come up with at least one example where you would try to minimize the force by stretching out the time. Talk to your neighbor. What can you come up with?
There's impact in
Racing, if you're sprinting, like you're going to,
Last time I did this, the cinder block came all the way over and my computer was covered with cinder dust.
that drives down the time to minimize your.
Okay. As hard as that was for me to get up on that, just try to imagine how hard it was before I lost the 60 pounds. That was awful. Okay. What examples can you come up with? Yes, sir.
The front of the car.
The front of the car has crumple zones? Yes, perfect. Okay. Other examples?
Shoot.
A parachute. Oh, yeah. That'd be a different experience, wouldn't it? Yeah. You want that parachute to stretch out the time that you're coming to a halt. The airbag we already talked about. What if what if when I was getting down from this, I just jumped and I locked my knees? Would that be a good thing to do? No, I want to, if I'm gonna be silly enough to jump off of that, I wanna bend my knees and lengthen out the time that I'm coming to a halt.
How does that crash make sense though? Because that happens in like half a second.
What's that?
Sledgehammer and the crash, like that happens in half a second. So
It did, but a half a second is so much better than 1 millisecond without the cinder block. It's 1,000 times better. Okay, so it's a game of inches, my friend. I have another example. When we were living in Seattle and I was at University of Washington with Lillian McDermott, the Relief Society president called up my wife and said, we're putting on a new roof. Could we borrow your husband? And my wife said, sure, I'm not gonna need him. And so she volunteered me. When I got there, I found out that their house was 2 stories tall. And I'm afraid of heights, and that just terrified me. There were all these manly men from the elders quorum that were up there walking around on this roof. And I got up there and I couldn't. I was just crawling around on my hands and knees. Well, one of the manly men brought his son named Christian, and Christian felt the same way I did. He was crawling around on his hands and knees. But unfortunately, he crawled right onto a piece of sheet metal that turned into a sled, and he went off of that roof and down on the deck below. Now, he grew up to be a fine young missionary, and he survived because it was a very, very old wooden deck, and he crashed through that wooden deck just like the sledgehammer crashed through that cinder block. And he was in the hospital for a while. He had broken bones, but he lived. Had it been a concrete patio, he would not be with us. Okay, that's an example. There's another whole class of situations where the force that we can deliver is fixed. We can only give so much force. And so we want to deliver that force for as long as possible to get the most change in momentum that we can possibly get. Get an example of that with your neighbor. Find an example of that. Okay. Let's share some examples. Raise your hand if you've got an example.
land on a trampoline. with that,
Okay,
so spread it out over time.
okay, you'd have more time to deliver the force. That's a little complicated because the force by the trampoline doesn't stay constant, as we saw in the exam. Other examples that you came up with? What about a rifle? Why do we make the barrel of a rifle long? So we can push on that bullet for longer to make it go faster. Okay. Same thing with the wrist rocket, those slingshots that have the really long surgical tubing. So it pushes when you hit a tennis ball, you want to keep contact with it for as long as possible. Those are some examples. Now, here's a wrinkle. My friend Jeff Adams and I are walking down the street, and suddenly one of our old students recognizes us and drops a couple of flower pots down on our heads. The flower pots come down at 20 meters per second. And in the case of Jeff, it bounces up at 20 meters per second. But in the case of Greg, it stops. Now, if these collisions take the same amount of time, that's an assumption. Who has the worse headache? Who experienced the greater force? And we're going to use our clickers to answer that.
But I don't know.
Okay, now you can click.
I feel like
the more energy, yeah, the energy those.
some of the energy.
How the other guy could have it. In like a rest.
Yeah, I didn't think about that. Okay, last call. Okay. You said, Jeff, Greg gets the kind of a toss up there. It doesn't surprise me that you're confused on that. And that's because I lied to you. I did, because you weren't ready for the truth. I told you that momentum was mass times speed, but indeed it is mass times velocity. It's a vector, and that vector nature is important. And that's one of the things that sets this apart from energy. We care very much about the direction. In other words, if I have a ball coming in at 50 miles an hour and the bat hits it out at 50 miles an hour, the incoming momentum before the collision and the outgoing momentum after the collision are the same size, but they're not the same momentum because they're in different directions. To find the change in momentum, I'd do what I'd always do, and that is I put them tail to tail, heel to heel. And I ask myself, what do I have to add to this initial momentum to the left to turn it into that final momentum to the right? Well, I have to add that change. There's the plus sign right there. I have to add a change big enough to bring this back down to zero and out the other way. Okay. Now that change is the impulse. The impulse causes the change. So they're the same size, and the impulse is just a name we give the force times the time. Now, if we look at the case for Jeff, the incoming momentum was down, the outcoming momentum was up. The change in momentum is twice the incoming momentum. But if we look at the case of Greg, it goes from the momentum down to nothing. And so it has half of the change. If the time is the same, that means half of the force. Another way of thinking of it is Greg's head just has to stop the flower pot. Jeff's head has to stop it and throw it back up. Okay. Now, in Montana, many months of the year, it's just icy. And Jeff and I were walking to our cars in the parking lot. As we crossed the street, a student in this great big huge old car tried to brake to a stop and just slid, just came sliding right through the intersection. Jeff and I quickly turned around, put our hands on the hood, and he pushed us all the way through the intersection. I was terrified. Jeff turned to me and said, "Is this one of your students or one of mine?" And so, okay, this is one of your homework problems that's due next Tuesday. You're welcome. You have this ball that is thrown against a wall at 15 meters per second, and it bounces away from the wall at 10 meters per second. Now we're told that the ball has a mass of 0.2 kilograms, and that might be different for you in your problem. That might be a parameter that is changed. Now, in this problem, we're told that the ball is in contact with the wall for 0.02 seconds, 2/100ths of a second. And we're asked to find the average force. Well, this is a momentum problem. If I look at the initial momentum, I have a mass of 2 kilograms and a velocity of 15 meters per second to the left, and that gives me 3 kilogram meter per second. What name do we give kilogram meter per second? A Newton meter we call a joule. What do we call a kilogram meter per second? Anyone know? It has never been named. And so we will call it the Francis. Okay, and so that would be 3 Franci. I have a lot of students. Eventually this is going to catch on. Now, after the collision, we have two franci to the right. Well, how different are three franci and two franci? And don't say one, because that's not the answer. Because we're looking for the difference between three franci to the left and two franci to the right. And that's going to be five franci to the right. There's the plus sign. That green arrow is what I have to add to the earlier momentum to turn it into the final momentum. Now, when I put that into my momentum equation, my delta P is 5. My time was given in the homework problem as 2/100ths of a second. And when I divide both sides by the time, I get 250 newtons. Okay? Now, folks, that's an old exam question. And when it was on an exam, a lot of people missed it by not adding, comparing the vectors like this. They just took the difference and got 1 instead of 5. Okay, don't let that be you. Don't let that be you. Let's talk about collisions. Suppose we have a truck hitting a Volvo, or I guess we could say that's a Volvo hitting the truck. And I use Volvos because no one gets hurt in a Volvo, okay? If I were to ask you during the collision to find the total impulse of the truck Volvo system during the collision, well, how would we do that? Well, since the impulse that we're looking for is the force times the time, and the force is a vector, I'm going to need a force on the truck and a force on the Volvo. Okay, so I'm going to draw free body diagrams. For the truck, I have weight down and normal by the road up. And for the Volvo, I have weight down and normal by the road up. I then have the normal force by the Volvo on the truck, and I have a much bigger normal force by the truck on the Volvo. I'll wait. I'm more patient than Captain Reagan. Okay. Someone going to call me a liar? Yeah, okay, you're willing. Okay, what's wrong with this picture? Oh, yeah, you held up 3 fingers. Newton's third law. Okay, these have to be exactly the same. It doesn't matter whether the truck is more massive or whether it was speeding or whether it was loaded with gold. By Newton's third law, they have to be exactly the same. So when I look at the impulse on the system, I've got the normal by the Volvo on the truck times the time, and the impulse on the Volvo is the normal by the truck on the Volvo times the time. Well, if this collision lasted for 1/10 of a second for the truck, it lasted for 1/10 of a second for the Volvo. So I can get rid of those indices. And now I know that this force is equal and opposite to that force. And I'm adding these as vectors. So this is always, always, always going to add up to 0. Now, if the impulse on that system is 0, what does that say about the change in momentum for that system? It doesn't change. The momentum is conserved. And that, my friends, is the very foundation of rocket science. That's what all of rocket science is built on. And this principle is built on Newton's third law. Okay, so Newton's third law is the foundation of rocket science. Now, my promise to you, and it's a conditional promise, if you always include everything in your system that bumps or bounces or hits, if you include everything in your system, the impulse on that system will always be 0 by Newton's third law. And in that case, the general equation, which is the momentum in the morning is equal to the momentum at night, except when it's not. And what changes momentum is impulse. But if I include everything in my system that bumps, that goes to 0. And I have momentum conservation. Now, what this means is that the momentum of the system initial is equal to the momentum of the system after. Now, a caveat, a little condition. With an energy problem, you got to choose what you meant by initial and what you meant by final. You can choose anything you want. But when you're dealing with a collision using momentum, these things have a specific meaning. Initial means right before the collision. Final means right after the collision. You can't wait for these cars to slide across the pavement and into someone's rose bushes, okay? Right before and right after. And the momentum's going to be conserved, okay? Now, example, I have two identical Volvos, each of 1,200 kilograms, each going 30 meters per second, about 60 miles an hour. And the question is, what is the total kinetic energy of that system? You're going to use your clicker, so get ready to use your clicker. I'm going to give you some choices here. One choice is 0, one choice is 36,000 joules, and one choice is 1,080,000 joules. So with your clicker, I'll get you started here. Now you can click.
Their kinetic energies are equal.
Okay, last call. It is rocket science. Okay. Okay, it's somewhere, it's either 0 or it is 1 million joules. Those are different than each other. Those are different than each other. Well, those of you that said 0, that's because this car has a whole bunch of left going energy and that car has a bunch of right going energy, and the left energy cancels the right going energy and I get 0. Is that what you were thinking? Except that there's no such thing as left going energy or right going energy. Energy is just energy. Like money, you got it or you don't got it, okay? And so this car has a bunch of energy, that car has a bunch of energy. I added up and the answer is C, okay? Let me show you with the math. If I look at the energy of the system, I add up the kinetic energy of the left car, which is 1/2 mv squared, and the kinetic energy of the right car, 1/2 mv squared. Now, you'll notice that for this car, I put a positive 30 because it's going to the right, and this one I put a negative 30 because it's going to the left. But right there, I just wasted, I guess I wasted shadow, whatever I wasted there, because I'm squaring it. Okay, so it doesn't matter. And so what I've got is 500,000 joules for the left, 500,000 joules for the right, and that gives me 1,000,000 joules. Now that's a lot of energy. Energy is the capacity to do damage. Those two cars have a lot of capacity to do damage. Yet this much energy would light a 100-watt light bulb for 10 hours. And you would expect to pay in Utah 4 cents for that, okay? What I'm trying to say here is that electric energy is cheap. I'm not telling you to leave your lights on when you don't need to, but I am telling you don't fight with your spouse about leaving the lights on. It's not worth it, okay? It's not worth it. Okay, now what about the momentum of this system? What is the total momentum of that system? Shout it out. 0, because now the direction matters. Now, when I look at the momentum, I need a coordinate system. And so the momentum of the left car is going to be mass times velocity. Momentum of the right car, mass times velocity. But now the plus sign and the minus sign mean something because I'm not squaring it. And so when I add that up, I get a total of 0 momentum. Now, if I include both of those cars in my system, that momentum of the system has to be conserved. And that means that after that collision, the momentum has to still be zero. So what's going to happen after the collision? What are they going to be doing after the collision? Is that zero momentum? Yeah. Is that the only way I can have zero momentum? No. They could bounce off going 30 meters per second the other way. That's zero momentum, or anything in between. Anything in between. Just because momentum has to be conserved in a collision doesn't mean there's only one way for it to be conserved. So we need to know some more information before we know which of these collisions are going to take place. Okay. Now, if I look at the energy of the system, I started with 1,000,000 joules of kinetic energy. In the first case, I lost all of it. In the bottom case, I kept all of it. In the middle case, I lost most of it. Now, let's talk about these cases, okay? Where does the energy go? Let's talk about this case here. Suppose you witnessed this collision. You were on the corner of the intersection where they collided. And the police came and they asked you, what did you see? What did you hear? What did it sound like? What did you hear? Anything? No, if you've still got all of your energy, sound is energy. If you didn't lose any of your kinetic energy, there's no sound energy. You can't hear this, okay? It's not going to heat up anything because heat's energy. So how would you make this collision on the bottom happen? What would you have to do to make that happen? Any ideas? Put it in a vacuum, okay? I'm still gonna, I won't hear anything because you can't hear you scream in the vacuum, but I would heat up the bumpers. My point is, this is not easy to make this happen. The only way I can think of is to put huge magnets on the hood of each car, North Pole against the North Pole, so that they never even touch. They come in and they go out. But what I'm saying is that that's really hard, okay? Now, where does the energy go? Most of the energy goes into messing up your car. A little bit goes into sound, a little bit goes into heating up the bumper, but most of it goes into messing up the car. We call that energy of deformation. And here's the thing. We don't have a formula for energy of deformation. It's just too messy, and it's different for every car and every angle of collision. So there's no sense looking for a formula. So we say that energy is conserved in all of these, but not the type of energy that we have formulas for, what we call mechanical energy. Okay? Now we give names to these collisions. If the energy, the mechanical energy, is conserved, we call that an elastic collision. If it is not conserved, we call it inelastic. And in the special case where the two bumpers lock together, making it one vehicle with 8 wheels, we call that maximally inelastic. Maximally inelastic. Those are the 3 flavors of collision. But hear me now. Momentum is conserved in all 3 flavors. Mechanical energy isn't. It's only conserved in the bottom one, and then only rarely once in a blue moon. But momentum is always conserved in every collision, and that's what makes it the most powerful tool to solving problems. Okay? Now, I'm, oh, they did not bring me my Uh, okay. Um, I asked for a steel slab, a rubber slab and a glass slab with a rubber ball, steel ball and a glass ball. And the question is, which collision is most elastic? I'll show this to you on Tuesday. Which is most elastic? Is it going to be the rubber on rubber, the steel on steel, or the glass on glass? What do you anticipate you will see on Tuesday when they actually bring me my demo?
Get rubber on rubber.
There's
Rubber on rubber makes sense.
Okay. Last call. Okay, we said rubber on rubber, as I knew you would. And what we're going to see on Tuesday when we actually have the equipment is that that's not the case. The rubber on rubber, well, how would you recognize a totally elastic collision? When you drop the marble or whatever from this high, how high would it come back? All the way back up. And if you drop a rubber ball on a rubber mat, it only comes up a little bit. If you do steel on steel, it comes even less. But if you drop, I actually do have glass. This is an award they gave me in Montana for teaching, so I'm going to finally get some use out of it. And a glass marble, it goes up the highest. It goes up the highest. And here's my point, the last point I'm going to make, folks. We use the word elastic in physics different than we do down at Staples. Elastic at Staples means rubber band, it stretches, it deforms. But in physics, it means don't lose the energy. And that happens because the glass doesn't deform. It's rigid. It doesn't put any energy into that deformation bucket. So why don't we stop here? You have a great weekend. Go to your tutorial.
Yeah.